Of the many reasons that pushed Germany to develop the twin-engine Ta-154 night fighter, two stand out above all. At the very beginning of World War II, the Luftwaffe simply had no purpose-built night interceptors. At the same time, a new threat emerged, the British Mosquito. Its all-wood construction not only made it fast and elusive, but also triggered a certain unease within the Reich Air Ministry. Germany now faced an aircraft that challenged both its technological pride and its assumptions about modern aviation. In response, German leadership set out to create something similar, but better. More powerful, more effective, and ideally capable of outperforming its British counterpart. For a long time, however, the public remained unaware of the complicated and often chaotic path this program would take. To understand why the Ta-154 appeared so late, it is necessary to look back at the mindset of the Luftwaffe before the war. German high command was deeply committed to offensive doctrine. The idea that enemy bombers could strike German cities at night was largely dismissed. Hermann Göring's confident claim that no enemy bomb will ever fall on Germany reflected this attitude and shaped early priorities. At first, reality seemed to support this confidence. German forces advanced rapidly across Europe, and the Luftwaffe dominated the skies. Yet even in 1940, the British had already begun a strategic bombing campaign. Early raids were limited in scale, but they carried an important message: Britain was not backing down. Night after night, the sound of distant engines and falling bombs began to erode the sense of security among civilians. Despite this, German leadership remained slow to react. The development of a dedicated night fighter was still not considered urgent. Instead, early night defense relied on improvised solutions. Under the command of Colonel Joseph Kammhuber, the first night fighter units were formed, using whatever aircraft were available. These included modified versions of existing bombers and heavy fighters. While far from ideal, these stopgap measures gradually improved as crews gained experience. At this stage, British bombers were relatively slow and poorly defended. Their tactics were predictable, often flying in long, loosely organized streams toward their targets. This made them vulnerable. German interceptors could pick them off one by one, and losses for the RAF sometimes reached unsustainable levels. These early successes created a dangerous illusion. German leadership began to believe that existing aircraft were sufficient, and that developing a new, specialized night fighter was unnecessary. Joseph Kammhuber strongly disagreed. He viewed these modified machines as temporary solutions at best, a way to hold the line until proper interceptors could be developed. However, his efforts faced resistance. Resources were limited, and priorities were divided. One of the key figures opposing him was Field Marshal Erhard Milt. As State Secretary of Aviation and later head of the Technical Office, Milch argued that production should focus on proven aircraft types. Germany was already suffering heavy losses on multiple fronts, and retooling factories for new designs seemed impractical. While debates continued, the situation in the skies grew more dangerous. A turning point came on the night of May 31, 1942, during Operation Millennium. Over 1,000 RAF bombers targeted Cologne, overwhelming the Kammhuber line, Germany's integrated night defense system of radar, searchlights, flak, and interceptor zones. The results were alarming. German defenses managed to shoot down only a small fraction of the attacking force. The limitations of the existing system became impossible to ignore. At this moment, hesitation gave way to urgency. The Reich Aviation Ministry finally issued a requirement for a new generation of dedicated night fighters. Major aircraft manufacturers, including Junkers, Heinkel, and Focke-Wulf, were tasked with developing entirely new designs. Junkers took a conservative approach, adapting existing bomber concepts. Heinkel revived an older heavy fighter project which would eventually evolve into the successful He-219. Focke-Wulf, however, was given a far more challenging task. They were instructed to develop a fast, two-seat night fighter built largely from wood, effectively Germany's answer to the Mosquito. Ironically, Kurt Tank had already proposed a similar concept earlier, but it had been rejected. Now, with British raids intensifying, the idea was suddenly seen as essential. The appeal of wooden construction was clear. It reduced reliance on scarce aluminum and allowed the use of alternative industrial resources. Yet this approach also raised serious concerns. Germany lacked both the skilled workforce and the experience needed for large-scale wooden aircraft production. Despite skepticism, Kurt Tank managed to push the project forward. Advances in adhesives such as the phenolic resin Tego Leim made it possible to create strong and reliable wooden structures. With official approval secured, the project moved ahead at an extraordinary pace. And from this moment on, the story of the Ta-154 becomes one not just of engineering ambition, but of relentless pressure, improvisation, and increasingly desperate attempts to keep up with a rapidly changing war. As work on new night fighters began, each company followed its own path. Junkers refined bomber-based concepts, while Heinkel pushed forward a more radical heavy fighter design. Yet the most demanding challenge remained with Focke-Wulf. They were now tasked with turning an already complex idea into a practical combat aircraft, a fast, two-seat interceptor built largely from wood, capable of operating in all weather conditions. What had once been an experimental concept suddenly became a priority project. At the same time, British Mosquito raids were growing increasingly bold. These aircraft struck deep into German territory, often with little warning, and disappeared before interceptors could even react. Their speed and altitude made them extremely difficult targets. This only reinforced the urgency behind the Ta-154 program. There was also a certain irony in the situation. The Mosquito, admired even by German engineers, became both a benchmark and a source of pressure. Field Marshal Erhard Milch, who had previously resisted new developments, now supported the idea of adopting similar design principles but improving upon them. The advantages of wooden construction were obvious. It reduced dependence on scarce strategic metals and allowed production to be distributed across industries not traditionally involved in aircraft manufacturing. However, this approach came with serious risks. Germany's woodworking industry was already under strain, skilled labor was limited, and most facilities were tied to existing contracts. Unlike metal airframes, whose structural limits could be calculated with precision, wooden structures introduced uncertainty. Variations in material quality, bonding strength, and environmental conditions all had to be considered. Despite these concerns, the project moved forward at an extraordinary pace. By September 1942, initial design work had begun in earnest. Within weeks, engineers finalized key calculations, and by mid-October, a preliminary design was ready for review. The proposed aircraft featured both single and two-seat variants, though the focus quickly shifted to the night fighter role. The material composition reflected the original vision. More than half of the airframe would be made of wood, with only minimal use of aluminum. This approach was approved, and by November, the project received full priority status. At this stage, the aircraft was still designated TA-211. However, Kurt Tank strongly disliked this numbering, likely due to its association with the unsuccessful Me-210. Soon after, the designation was changed to Ta-154, marking the beginning of a new chapter. Development was led by a small but experienced team. Senior engineer Ernst Knipp oversaw the project, supported by specialists in aerodynamics and structural design. Together, they began refining the aircraft into a workable form. One of the first major changes was the wing configuration. The original mid-wing layout was abandoned in favor of a high-wing design, which offered structural and aerodynamic advantages. The wing itself was constructed as a single wooden piece, providing both strength and simplicity. The fuselage followed a similar philosophy. Built as a monocoque wooden structure, it housed a tandem crew arrangement in the forward section. The canopy design prioritized visibility, while the tail assembly remained clean and aerodynamically efficient. Another unusual feature was the landing gear. Instead of the traditional tailwheel configuration, the TA-154 used a tricycle arrangement with a nose wheel. Although uncommon at the time, this design improved ground handling and forward visibility during takeoff and landing. Power came from a pair of Jumo engines, which were already in large-scale production. This decision simplified logistics, but it also imposed certain limitations on performance. From the very beginning, time was the enemy. The Reich Air Ministry demanded that the first prototype be ready for flight testing by mid-July 1943. This left less than a year to complete design, construction, and initial testing, an almost impossible timeline. To meet these demands, work proceeded on multiple fronts simultaneously. While engineers finalized drawings, factories began preparing production lines. Components were manufactured even before testing procedures were fully established. This approach accelerated progress, but it also introduced risks. Structural testing quickly revealed weaknesses in the wooden airframe. Under concentrated loads, the material showed a tendency to crack and splinter. Reinforcing these areas with metal proved difficult, as bonding different materials reliably was not yet fully understood. In response, engineers developed alternative solutions. High-stress sections were reinforced using compressed wood and early composite materials such as lignofol and dinyl. These materials offered improved strength while maintaining compatibility with the overall structure. At the same time, innovative testing methods were introduced. Researchers discovered that towing airframe components underwater could simulate aerodynamic forces experienced in flight. This led to a series of unusual experiments where sections of the aircraft were dragged through lakes to measure stress and resistance. While unconventional, these tests provided valuable data in a short amount of time. Meanwhile, assembly of the first prototypes continued. Factories worked around the clock, with parts arriving from multiple locations. The entire process resembled a race against time, where delays in one area immediately affected all others. Inevitably, problems began to accumulate. One of the most serious issues was weight. As new systems were added, the aircraft became heavier than originally planned. This reduced performance and placed additional strain on the engines. The intended solution was to use more powerful Jumo 213 engines. However, these were not yet ready for deployment. As a result, early prototypes had to rely on older engines, limiting their capabilities. Despite these setbacks, the first prototype, the Ta-154V1, was completed in the summer of 1943. It lacked radar, armament, and several operational systems, but it was sufficient for initial flight testing. In early July, the aircraft took to the skies for the first time. The flight itself revealed both promise and problems. Shortly after takeoff, the aircraft showed unstable behavior, requiring constant correction from the pilot. Hydraulic issues prevented the landing gear from retracting properly, forcing the crew to rely on emergency systems during landing. Yet, despite these difficulties, the aircraft demonstrated good overall handling characteristics. Control response was smooth, and the general flight profile was considered acceptable. This combination of potential and instability would come to define the Ta-154 program. From this point onward, each test flight brought new data and new challenges. Engineers worked continuously to refine the design, while pilots pushed the aircraft to its limits. The pace did not slow down. If anything, it only intensified. And as the testing program expanded, the gap between expectations and reality became increasingly difficult to ignore. As testing continued, additional prototypes were brought into the program. Each new aircraft introduced incremental improvements, but also revealed new complications. The Ta-154 was evolving, though not always in the direction its designers had hoped. With the installation of onboard radar systems, the aircraft began to take on its intended role as a night interceptor. This added both capability and complexity. The FUG-212 radar, along with its distinctive antenna arrays, increased drag and further reduced speed. At the same time, it placed additional strain on the already limited power output of the engines. Nevertheless, these systems were essential. Without radar, the aircraft could not operate effectively at night, making this compromise unavoidable. Armament was also gradually introduced. The Ta-154 was designed to carry a combination of 20mm and 30mm cannons, giving it significant firepower against bomber formations. In theory, this made it a formidable opponent. In practice, however, performance remained inconsistent. The added weight of radar, weapons, and reinforced structures continued to push the aircraft beyond its original limits. Climb rate suffered, maximum speed dropped, and overall agility declined. Pilots reported that while the aircraft was manageable, it lacked the decisive performance needed to intercept faster targets like the Mosquito. At the same time, a new and unexpected problem began to emerge, one that would ultimately prove far more damaging than any aerodynamic flaw. The issue lay not in the design itself, but in the materials used to build it. The Ta-154 relied heavily on a specialized adhesive known as Tego Leim. This glue was critical for bonding wooden components and ensuring structural integrity. It had been carefully selected during development and performed reliably in early prototypes. But in the summer of 1943, disaster struck. The factory producing Tego Leim was destroyed during an Allied bombing raid. With supplies cut off, manufacturers were forced to find alternatives. A substitute adhesive was introduced, one that appeared suitable on paper but had not been fully tested under operational conditions. The consequences were severe. Aircraft built with the replacement glue began to show signs of structural failure. Bonded joints weakened over time, especially under stress and changing environmental conditions. In some cases, sections of the airframe began to separate entirely. This problem was difficult to detect during initial inspections, making it even more dangerous. Failures could occur suddenly without warning. As reports accumulated, confidence in the aircraft declined rapidly. At the same time, the broader situation within Germany was deteriorating. Allied bombing campaigns intensified, targeting industrial infrastructure and disrupting production across the country. Supply chains became unreliable and delays increased. Under these conditions, maintaining consistent quality became nearly impossible. Despite these setbacks, efforts to bring the Ta-154 into operational service continued. Several pre-production aircraft were delivered to evaluation units, where pilots tested them under combat-like conditions. Their feedback was mixed. While the aircraft offered good visibility and stable handling, its performance limitations and structural concerns could not be ignored. In comparison, the Heinkel He-219, developed in parallel, was already demonstrating superior capabilities. It was faster, better equipped, and more reliable in combat conditions. Gradually, priorities began to shift. Resources that had once been allocated to the Ta-154 program were redirected toward more promising designs. Production plans were scaled back and expectations were lowered. For Kurt Tank and his team, this marked a turning point. What had started as an ambitious attempt to match and surpass the Mosquito was now struggling to justify its existence. The combination of material shortages, technical challenges, and changing priorities left little room for recovery. Even so, development did not stop immediately. Engineers continued to experiment with improvements, including alternative engines and structural reinforcements. Some later variants showed potential on paper, but few progressed beyond the prototype stage. By early 1944, the fate of the Ta-154 was becoming clear. Production numbers remained low and operational deployment was limited. The aircraft never reached the scale originally envisioned by its designers or the German High Command. Instead, it became another example of a promising concept, undermined by circumstances beyond engineering alone. In the end, the Ta-154 was not a complete failure, but neither was it a success. It demonstrated innovative ideas, particularly in the use of wood and alternative materials. It showed that rapid development under pressure was possible, but it also exposed the risks of relying on fragile supply chains and unproven production methods. And perhaps most importantly, it highlighted a broader reality of the war. By the time the Ta-154 was ready, the conditions that had led to its creation had already changed. The Luftwaffe was no longer in a position to dictate the pace of technological development. Instead, it was reacting, often too late, to an enemy that had already adapted. In that sense, the Ta-154 was not just an aircraft. It was a reflection of a system under strain, trying to innovate while resources dwindled and pressure mounted from all sides. And like many such projects of the time, it arrived with promise, but ultimately without the opportunity to fulfill it.